I think the danger of AI is much greater than the danger of nuclear warheads, by a lot. Mark my words, AI is far more dangerous than nukes.
Ever wondered what might happen if we brought together two revolutionary technologies, AI and quantum computers? Recently, the US government stumbled on something unsettling and has taken an intriguing step, urging Google and NASA to halt their quantum computer development efforts. This is something that renowned physicist Michio Kaku has been warning about for years. What's going to happen? Join us today as we uncover the truth about quantum computers and AI.
So the two of them, the chatbots that are a revolution in software, and then quantum computers, which are a revolution in hardware, when they get together, watch out. So we're talking about an extremely powerful alliance between software and hardware.
Quantum computers are highly fascinating machines that operate based on the principles of quantum mechanics. Unlike our familiar traditional computers, which use bits to represent information as zeros or ones, quantum computers work with qubits. Now, these qubits are a whole different ballgame. They can hold information as both 0 and 1 at the same time, thanks to a wild phenomenon called superposition. Qubits are the rock stars of the quantum computer world. They can exist in multiple states simultaneously, all thanks to their superposition powers. This means that quantum computers can crunch through complex calculations in parallel, potentially speeding things up exponentially compared to our classical computers. But wait, there's more. Entanglement is another mind-blowing trick up the quantum computer's sleeve. It's like magic that connects multiple qubits together. When entangled, the state of one qubit becomes intimately linked to the state of another, no matter how far apart they are. It's like they have a cosmic connection. So, quantum computers aren't your run-of-the-mill machines. They harness the extraordinary abilities of qubits to compute things in an entirely different league. Traditional computers use classical bits and can only go one step at a time, either 0 or 1. But quantum computers tap into the superposition and entanglement phenomena to process oodles of information all at once. Talk about multitasking on a galactic scale. Now, if you're wondering where this quantum revolution began, well, it all traces back to the early 20th century, when the captivating quantum theory took its first breath. Since then, scientists have been on a thrilling endeavor to unlock the true potential of quantum computing. Quantum theory is like a wild adventure into the tiniest building blocks of our universe, atoms and subatomic particles. This branch of physics brought in a whole new perspective called quantum mechanics that turned classical physics upside down and inside out. Back in 1900, Max Planck took the stage with a radical idea. He proposed that energy is not a smooth and continuous flow, but rather comes in discrete little packets called quanta. Imagine energy as tiny energy snacks. This groundbreaking concept laid the groundwork for understanding that particles, like electrons, can only exist at specific energy levels, no in-between shenanigans. Then, in 1925, Werner Heisenberg added to the quantum commotion with his famous uncertainty principle. It's like saying, hey, you can't have it all at once. According to Heisenberg, we can't pin down the exact position and momentum of a particle simultaneously. The quantum world loves its surprises, keeping us on our toes and embracing probabilities. In 1935, the plot thickened with Albert Einstein and his buddies Boris Podolsky and Nathan Rosen. They cooked up the EPR paradox, a thought experiment that would make your head spin. They raised the idea of spooky action at a distance, where entangled particles seem to communicate faster than the speed of light, no matter how far apart they are. It's like quantum teleportation, and it gave us all a good dose of scientific goosebumps. But the party was just getting started. It wasn't until 1980 that the revolutionary concept of quantum computing popped up on the scene. We're talking about computers that harness the mystical powers of quantum mechanics to do some seriously mind-blowing calculations. In 1982, physicist Paul Benioff had a light bulb moment. He envisioned a whole new breed of computers harnessing the incredible power of quantum mechanics. Yep, We're talking about quantum systems performing mind-blowing computational tasks, making our regular computers look like snails in comparison. But the quantum computing fever didn't stop there. In the same year, physicist Richard Feynman got all fired up and expanded on Benioff's ideas. He saw the potential of quantum computers to tackle problems that our classical computers would just throw their hands up at and say, "No way, I can't deal with this." Feynman's visionary thinking ignited a bonfire of curiosity in the scientific community, laying the groundwork for further exploration and research in the field of quantum computing. Throughout the following decades, researchers rolled up their sleeves and dug into the nitty-gritty of quantum mechanics, understanding the principles that underpin this technology. Then, in 1994, the math wizard Peter Shor pulled a rabbit out of the quantum hat. He developed a groundbreaking algorithm that showcased the true potential of quantum computers. It's like he cracked a secret code allowing quantum computers to factor large numbers in a snap, way faster than our classical computers could even dream of. The year 1998 brought us the first glimpse of a real, practical quantum computer. A team of researchers at the Los Alamos National Laboratory crafted a 2-qubit quantum computer using fancy-sounding nuclear magnetic resonance techniques. Sure, it had its limitations, but it was a crucial milestone in the quantum computing journey. Forward to the early 2000s, the era of quantum computing progress. Multiple research groups and companies were on a mission to craft even more sophisticated quantum computers. And they did deliver some breakthroughs. In 2001, the IBM team hit the jackpot. They proudly presented the IBM Qubit, a 7-qubit quantum computer that left scientists and tech enthusiasts in awe. And then, the quantum community got busy with something called quantum error correction. You see, qubits can be a little fickle. They interact with their environment and can lose their quantum charm. So, researchers put their thinking caps on and came up with clever codes, like the surface code, to protect quantum information. It was like giving qubits a sturdy quantum armor, making quantum computers more reliable and robust. Fast forward to 2005, and researchers at the University of Innsbruck and the National Institute of Standards and Technology, NIST, achieved a remarkable feat. They assembled a working quantum computer with 5 qubits. Now you might think, only 5 qubits? What's the big deal? But trust me, it was a quantum leap. This small yet mighty machine proved that practical quantum computers were within our reach. The quantum train didn't stop there. In 2007, scientists at Yale University cracked the code to create stable qubits using solid-state systems. You know, materials that are more stable and easier to handle. It was like finding a new recipe for quantum stability and paving the way for more user-friendly quantum computers. In 2010, the University of Science and Technology of China pulled off something straight out of sci-fi: quantum teleportation. No, not beaming people around, but teleporting the quantum state of one particle to another particle, far away, 10 miles to be precise. This was epic because it showcased the potential for building quantum networks, where quantum information could travel great distances, like a quantum postman doing its rounds. In the year 2013, a powerful collaboration between Google and NASA took shape. They teamed up to develop a groundbreaking quantum computer named the D-Wave 2. The plan was to set up this cutting-edge technology at NASA's Ames Research Center, ready to conquer new frontiers. But just as the project was gaining momentum, an unexpected hurdle appeared on the horizon. The government decided to put the brakes on Google and NASA's quantum computer development efforts, leaving the project in a state of uncertainty. Imagine a car revving its engine but unable to hit the road. It was frustrating, to say the least. The D-Wave 2 quantum computer was all powered up and ready to work its magic, but its future was suddenly unclear. The tricky part was that turning the computer off and on again when things returned to normal would be a costly and time-consuming endeavor. So, although the computer was humming with electricity, it couldn't be used to its full potential. For Google, things got a bit confusing too. They had invested in the special Ames Quantum Artificial Intelligence Lab, which granted them access to the quantum computer. But with the lab closed, they found themselves at a loss. The computer was working, but they couldn't fully utilize it. and their future plans remained uncertain until NASA was back up and running. The government shutdown took its toll on the project, forcing NASA's testing and exploration of this exciting technology to come to a halt. Time was lost, and opportunities slipped through their fingers. The passionate folks working on the project were disappointed that progress had hit a roadblock. But don't feel too bad. The story doesn't end here. With government operations back on track, the D-Wave 2 quantum computer and the dream of exploring the quantum frontier will surely bounce back with renewed energy. In 2019, Google took the world by storm yet again, hitting the headlines with an astonishing achievement: quantum supremacy. They unleashed their secret weapon, the mighty Sycamore quantum processor, to tackle a mind-boggling mathematical problem. You won't believe it, but this problem would have kept our regular computers busy for thousands of years. This breakthrough sent shockwaves through the tech world, revealing the true might of quantum computers for certain tasks. Other tech giants like IBM and Microsoft were inspired to roll up their sleeves and dive headfirst into the quantum realm. It became a quantum race, a competition to build better and more reliable quantum systems. Then, in 2020, IBM stepped up with a game-changer, the IBM Q System 1, the first fully integrated quantum computer designed for commercial use. This was a big deal. It meant that quantum computing was getting practical and accessible for a wider range of applications. Quantum computing research was on fire, attracting attention and investments from governments and industries worldwide. Governments couldn't resist the quantum allure and recognized the game-changing potential of these computers. So they provided funding for exciting quantum research initiatives. This led to the birth of quantum research centers and labs, becoming hotspots for collaborations between academia, industry, and government agencies. Modern scientists have a hunch that intelligent life might be out there, roaming on other planets. But here's the catch. They could be using black holes as powerful supercomputers. You see, the Fermi paradox has been boggling the minds of scientists for ages. If there's a good chance that life exists elsewhere in the vast universe, why haven't we stumbled upon clear evidence of it? It's like searching for a needle in a cosmic haystack. Now, the Hart-Tipler conjecture tried to explain this cosmic puzzle, suggesting that if advanced alien civilizations were out there, we'd spot signs of their activity all over the place. But here's where things get even more intriguing. A group of German and Georgian physicists threw in a new idea. They proposed that maybe these clever civilizations are using black holes as their ultimate supercomputers, powering up their vastly advanced technology. Since 1960, scientists have been on the hunt for extraterrestrial intelligence, scanning the cosmos for radio signals from far-off star systems. But what if that's just the tip of the space iceberg? Some researchers believe it's time to broaden our search, keeping our cosmic eyes peeled for other signs of technology. Thinking directed energy neutrinos, quantum communications, and even gravitational waves. But back to the study by Gia Dvali and Zaza Osmanov. These folks think big, exploring the idea of large-scale quantum computing as a potential clue to finding these advanced alien civilizations. Quantum computing is a real game-changer, boasting significant advantages like lightning-fast information processing and near-impenetrable security. With how rapidly this technology is advancing, it only makes sense to believe that advanced civilizations would make the most of it. But where would they do it? Scientists have an intriguing theory. It could all be happening in black holes. You see, black holes, those cosmic enigmas, provide the perfect playground for quantum computing based on the laws of quantum physics and gravity. In simple terms, it's like a tailor-made spot for quantum wizardry. These hypothetical black holes, probably crafted by these advanced aliens, would be teeny tiny to boost computing efficiency. And as a result, they would unleash intense radiation, including a special something called Hawking radiation. Now let's talk about this fascinating concept, Hawking radiation, named after the late physicist Stephen Hawking. According to his theory, radiation is released just outside the boundary of a black hole due to quantum effects. Dvali and Osmanov, the brilliant minds behind this idea, suggest that this radiation, including Hawking radiation, could actually be a telltale sign of these advanced alien civilizations. But what's so special about this radiation? Well, it consists of tiny particles, including high-energy neutrinos. Now, neutrinos are like sneaky cosmic couriers. They can go through almost anything, making them perfect carriers of information and nearly impossible to block. According to the researchers, these high-energy neutrinos might come from both the Hawking radiation of small black holes and the particle collisions used to create them. To keep an eye out for these cosmic signals, the Ice Cube Observatory, buried deep in Antarctica's ice, comes into play. It could be a crucial instrument to detect these telltale signs of advanced technology. This groundbreaking theory might just be the key to solving the famous Fermi paradox, the mystery of why we haven't found any signs of advanced civilizations yet. If these cosmic neighbors have moved beyond traditional radio and digital communication and started using black holes as their quantum supercomputers, it totally explains why we haven't stumbled upon their technology yet. And with the rapid progress of computing, it's possible that they might only use radio signals for a limited time. It all fits into the L parameter in the Drake equation, the representation of how long civilizations actively send detectable signals into the vast cosmos. Michio Kaku, the rock star scientist of theoretical physics. This genius not only delves into mind-bending string theory, but also has a superpower, the ability to make complex scientific concepts sound like a walk in the park. And guess what? In his recent book, Quantum Supremacy, he takes us on a thrilling quantum adventure. But that's not all. This scientist also popped up on a recent podcast episode. So, Dr. Michio Kaku explained something mind-blowing. You see, AI chatbots are pretty nifty. They can generate all sorts of thoughts and ideas. But here's the catch. They struggle with the age-old question of what's true and what's false. That's where quantum computers come in to save the day. These quantum beasts have the power to check the accuracy of information created by AI systems, giving us more reliable results. But hang on a sec. Dr. Kaku has some worries too. He's concerned about who gets to control this fact-checking superpower. You know, governments could potentially manipulate information and suppress opposing viewpoints. It's like a cosmic tug of war, and we need to make sure we're on the right side. Now let's talk about the great double-edged sword that is quantum computing. On one hand, it has the potential to massively benefit society. But if used for mischief and deception, it could turn into a tool for controlling and manipulating information. The development of AI has been like a rocket to the stars, zooming ahead with impressive progress. We now have AI image generators and chatbots that are mind-blowingly advanced. But hold up, there are dark corners lurking in this high-tech wonderland. We've got deep fakes spreading false political information like a cosmic wildfire. The ability to create super-realistic images, videos, and audio recordings raises serious questions about evidence and authenticity. It's like stepping into a cosmic hall of mirrors, where truth gets distorted. Those pesky deep fakes can be used to stir up chaos by fabricating orders and misinformation in international conflicts. Law enforcement AI tools can also add to the problem, leading to excessive policing and biased decision-making, particularly affecting marginalized communities. The bias in AI models only adds fuel to the fire, worsening inequality. Even AI language models can be troublemakers, generating false information that might cause harm. Oh, and don't forget about those sneaky AI trading bots, playing havoc with the stock market. But no need to panic. Scientists worldwide are on a mission to build the ultimate quantum computer. It's a challenging task, and it might take several more years, maybe even a decade, to make it a reality. The timeline depends on technological breakthroughs, new discoveries, and of course, having enough resources to pull it off. Now, they're using two main approaches. First up, gate-based quantum computing. It's like controlling individual quantum bits, aka qubits, to perform calculations. They're working hard to create more stable qubits, like superconducting circuits and trapped ions, and finding ways to minimize errors and fix mistakes. Then there's adiabatic quantum computing, which involves gradually evolving a quantum system to solve complex problems through a process called quantum annealing. They're experimenting with different materials and specialized devices to boost the performance and scalability of adiabatic quantum computers. But it's not all smooth sailing. Quantum computers are a bit delicate. They get easily affected by their surroundings, leading to errors. Scientists need to maintain these delicate quantum states, called quantum coherence, for proper computation. Plus, these quantum beasts demand a highly controlled and isolated environment with super low temperatures. Yep, it's tough and pricey to create and maintain these conditions. Scaling up quantum computers is like walking on a tightrope. It's a tricky engineering challenge. Error correction is a crucial piece of the puzzle in the world of quantum computing. Scientists are hard at work, exploring ways to tackle those pesky errors that sneak into quantum computations. Errors can be like that pesky neighbor, annoying and persistent. And to make things trickier, they can worsen over time, messing with the accuracy of our results. Implementing error correction might add a dash of complexity to the hardware requirements, but they won't back down. They're coming together like a coalition, governments, academic institutions, and private companies, uniting to invest heavily in quantum research and development. Initiatives like IBM Quantum, Google Quantum AI, and Microsoft Quantum are leading the way, providing researchers worldwide with access to top-notch quantum hardware, software, and educational resources. But that's not all. This quantum adventure is full of continuous innovation. Scientists are cooking up fresh quantum algorithms and software, bringing us one step closer to the quantum wonderland. Now let's talk applications. Quantum computers are bursting with potential in various fields. They're like cosmic superheroes, ready to take on optimization problems, machine learning, cryptography, and even drug discovery. It's like having a supercomputer with quantum superpowers capable of outperforming classical computers. Quantum computers will easily revolutionize our understanding of the cosmos. In the realm of space exploration, they hold tremendous potential to enhance our simulations and modeling of astronomical phenomena. Imagine those complex space missions involving intricate calculations and simulations to decipher the mysteries of celestial bodies and their cosmic interactions. Well, quantum computers have got our back. They can perform these mind-boggling simulations faster and more accurately than our traditional computers, giving us deeper insights into the behavior of galaxies, black holes, and all those cosmic wonders out there. This means we can plan space missions with greater precision, optimize trajectories, and predict the movements of space debris. The result? Improved mission success rates and better safety for our cosmic voyages. But hold on tight, because quantum computers are about to shake up the world of cryptography too, a vital aspect of space exploration. You know, secure communication and data transmission are crucial for space missions, especially when it comes to protecting sensitive information from prying eyes and tampering. Traditional cryptographic algorithms like RSA and AES have relied on the challenge of factoring large numbers to keep data secure. But here's the catch. Quantum computers are absolute pros at factoring those large numbers, thanks to their parallel computation magic. Quantum cryptography is here to save the day, riding on the wings of quantum mechanics. By harnessing the fundamental properties of quantum particles, think entanglement and superposition, quantum cryptography creates secure communication channels that guarantee the integrity of transmitted data. In space exploration, quantum computers bring a boost to secure communication protocols, protecting critical information from prying eyes and unauthorized access. But that's not all. They've got some cosmic tricks up their sleeves too. Quantum mechanics blesses them with amazing phenomena like quantum entanglement and quantum tunneling. And trust me, these phenomena are no joke. Quantum tunneling, for instance, allows particles to slip through energy barriers, potentially paving the way for more efficient and speedier spacecraft propulsion. Imagine zipping through space like a cosmic racer, exploring distant celestial bodies with ease. By simulating and studying these quantum wonders, our brilliant scientists can design revolutionary propulsion systems, unlocking new horizons of space exploration. But it doesn't end there. Quantum computers are here to lend a helping hand to the military too. They're like cosmic code breakers, cracking encryption algorithms with ease and strengthening secure communications. But wait, there's more. Quantum simulation and modeling are cosmic genies, optimizing logistics, designing materials, and even simulating nuclear reactions. And that's not all. Machine learning on quantum computers enhances decision-making, pattern recognition, and autonomous systems. They're like cosmic problem solvers, tackling optimization challenges to aid in mission planning, and smartly allocate resources. And let's not forget the quantum sensors. They're like cosmic trackers, improving target detection and tracking with precision. And with quantum communication guarding the channels, it's like having a cosmic security system for real-time battlefield analysis and data processing. That's situational awareness at its finest, empowering informed decision-making on the cosmic battlefield. Sure, quantum computing is still unfolding like a cosmic mystery, but it holds the promise of unlocking immense potential for enhancing military capabilities. While quantum computers offer exciting possibilities for scientific breakthroughs and advancements in various fields, they also come with potential threats and challenges that need our attention. The most significant concern revolves around the threat they pose to encryption systems, a fundamental tool in securing sensitive information and protecting data privacy. Many secure communication protocols, like those used in online banking and government agencies, rely on the complexity of factoring large numbers into their prime factors. Classical computers struggle with these calculations, making encryption pretty secure. But here's where quantum computers shake things up. They have the potential to break these encryption schemes using Shor's algorithm, which can factor large numbers quickly. If quantum computers fall into the wrong hands, our confidential information, like financial records or classified data, could become vulnerable to malicious attacks. Another area of concern lies in the world of cryptocurrencies. You've probably heard of Bitcoin, right? Well, cryptocurrencies use cryptographic algorithms, like the elliptic curve digital signature algorithm, to secure transactions and maintain the integrity of the digital currency. But guess what? Quantum computers could break these algorithms too. And if they become powerful enough, they might just undermine the trust and reliability of cryptocurrencies. Imagine the chaos in the digital economy that could follow. So, as we delve deeper into the quantum world, we must address these encryption challenges head-on. Scientists and experts worldwide are working tirelessly to develop new cryptographic methods, known as post-quantum cryptography, to defend against potential quantum threats. This cosmic battle between quantum computers and encryption is like a never-ending dance, but we're determined to keep our data secure and our digital economy stable. Quantum computers, though promising, also bring forth potential threats to the very fabric of the internet. The internet's security relies heavily on public key cryptography to protect online communication, transactions, and data transfers. But here's the cosmic conundrum. Quantum computers have the power to break encryption algorithms, rendering these security measures ineffective. Imagine sensitive information exposed and cyber attacks becoming rampant, shaking the foundations of e-commerce, online banking, and the overall trustworthiness of our digital interactions. And there's more. Data privacy is under scrutiny too. With their immense computational prowess, quantum computers could unravel patterns and correlations hidden within large datasets, even if they're encrypted or anonymized. This could be cosmic chaos for individuals and organizations relying on data privacy to safeguard personal information or trade secrets. We're talking about potential breaches of data privacy, raising concerns about ethics and the need for regulatory frameworks to protect our rights and prevent the misuse of sensitive information. Quantum computers can even shake the foundations of scientific simulations and models. Their power could potentially undermine the integrity of these simulations, leaving scientists and researchers with uncertainty. Quantum simulations hold cosmic potential, promising revolutionary advancements in fields like material science, drug discovery, and climate modeling. But let's stay grounded, because here's the concern. If quantum computers grow powerful enough, they might break through the encryption protecting these simulations. Imagine unauthorized access to sensitive information, or worse, altering the results. This cosmic conundrum could seriously impact scientific research, innovation, and decision-making. But don't panic just yet. Our cosmic heroes are already at work, as said earlier, devising proactive measures to protect us from these quantum threats. They're exploring post-quantum cryptography, developing encryption algorithms that can stand up to quantum computer attacks. However, making the transition to these new methods will require careful planning and coordination to ensure the security of our existing systems. We need investments in quantum-resistant technologies and encryption standards to stay one step ahead of the game. Governments and organizations must join forces to develop robust solutions and establish guidelines and regulations to protect our sensitive data from the quantum onslaught.